Okay, welcome to Note Set 10, where we'll be talking about this idea of elimination, except now doing it using matrices, and we can take advantage of what we've just learned about matrix multiplication. That's the main reason why we introduced matrix multiplication in the previous note set, but as I said, multiplying two matrices shows up all over the place in linear algebra, so it wasn't just for this idea that we learned that. But we needed to have it done before talking about this particular topic. So the stuff we're going to talk about here is in section 2.3. So remember, our focus in most of the course is solving this matrix equation. A is known, B is known, and we need to find the x. And remember, our view here is that we had the row view and the column view. So the row view says that each row defines a hyperplane, and we're looking for the x that defines the point where all of those hyperplanes intersect, if they do intersect at all. But the column view, which is the more theoretically powerful and insightful way of thinking about it, says we're looking for the coefficients in x that will be or the values in x that will be the coefficients in front of the columns of A in a linear combination of those columns that will add up to give B. What we're really doing is looking for focusing on the mechanism by which we solve this, not how we think about it. So here we're just simply interested in some machinery to get the final system into an upper triangular form so that we can solve the bottom equation very simply, and then back substitute to the next to last equation and solve for one more variable, and so on and so on and so on, and just keep back substituting. So since it's in a upper triangular form, the bottom one has one variable to solve, and then when we go up one, we still have just one unknown variable to solve, and every time we go up one equation, we know all but one of the variables, and so it becomes a single variable problem to solve. That's the idea. So we looked at how to do this by identifying pivots, identifying the coefficient on the equation to be modified, using those to form the appropriate multiplier, multiply an equation and then subtract it, and so on. And what we want to do now is show that we can do this by just using matrix multiplication with appropriately chosen matrices. So, like I said, and now we'll recall some more of the details here. We identify the pivot, and we talked about how we may have to interchange positions of equations if we reach a case where the pivot is 0. We may be able to fix that 0 pivot case by swapping the position of equations. Use the pivot to determine the multiplier, and then use that multiplier with subtraction to eliminate one of the variables. And so the idea is we go from some general system that looks like this to a system that looks like this, where we have an upper triangular system. So here's our diagonal with the pivots on them, and we have only stuff above that diagonal. So that's what we did before, and what we want to do now is illustrate how we can do elimination using matrices. So instead of having to manipulate equations, we can manipulate the matrix A and the vector B. And so this makes it straightforward to actually do this numerically. We just have to store the matrix A and the vector B in principle separately, although at the end of the notes we'll see how we can slam both of those into one bigger matrix and work with them both directly. Okay, so here we show the system that we were just looking at, and we show how it is converted into a matrix A and a vector B. And so the first step that we've seen before, we identify our pivot 2, we identify the coefficient. So the multiplier ends up being the coefficient 4 divided by 2, so the multiplier is 2, and then we have the negative from the fact that we're subtracting, so that we cancel that the 4 here. And so if we imagine creating a matrix, and we'll use the symbol capital E for these matrices to evoke the idea that they're elimination matrices. And what we're going to do is multiply both sides of this matrix equation up here by this matrix. And you'll notice that we have a sub 2, 1 here. That's telling us the position where we're going to put the negative of the multiplier. So remember, we figured out that our multiplier was 2, and so we put in the negative of the multiplier here to be negative 2. And its position has to do with what equations we're working with. So we are trying to create a new equation 2, so that's why it's in this second row, and we're working with equation 1. Equation 1 was the thing that gets multiplied, and so that would be column 1. And so where they intersect is where we are going to put this one single number. And you can kind of see that everything else in that matrix is just the elements of the identity matrix, right? So if we replace this negative 2 by 0, we would have the identity matrix. So that's the basic idea. But you can also verify that, when you multiply this, if you do it carefully and watch the effect of this matrix on the elements, you can see why we need to have that negative 2 there. But when we multiply that, you can see the effect. So here is what happens after we do that step, and you can see that the first equation remains unchanged, obviously, because what we're doing is creating the new equation number 2. And you can see that when we do this step here, we end up with a 1x2 and a 1x3, and we end up with a 4. So the 2 and the 10 over here stay the same. And you can see that we've accomplished that same exact thing over here. We've got a 0, 1, 1 in the second row. That corresponds to a 0 times x1, 1 times x2, 1 times x3, and we've got a 4 over here, and that matches the 4 that we had there. So if you, actually do the by hand method of multiplying this EECE212 times the given A, and then also times the given B, and kind of watch the machinery work, you'll see how it is that actually happens, and how that's equivalent to this taking equation 2 and subtracting 2 times equation 1 from that. So I'm just showing here in symbols how we would notate this. So we've converted this into a new system. And this is where the proof of elimination being a valid approach would actually stem from this viewpoint. We're not quite there yet to be able to do that proof, and we will not do that proof, because the point of this course is not about seeing all the proofs. So we have to enter in with a certain amount of trust and belief, but nonetheless, it would be this mechanism, now that we have this representable in terms of matrices, that would allow us to do an easier version of the proof of why this is valid. But it's kind of like, if we take a scalar equation and we multiply each side by some non-zero value, then we've not really changed the solution to that equation. And that non-zero value in the matrix world would mean that these things have to be non-singular or invertible. So remember we talked about inverses and singularity and non-singular and so forth. So non-singular means that they are invertible, and so that, as we mentioned earlier, kind of plays the role of being like not zero in the scalar sense. So that kind of roughly sketches how we would attack demonstrating or proving that this approach does not change the solution of the equations, and so is therefore valid. Now, I would encourage you to actually physically do this multiplication so that you can verify these results and practice doing that. So let's continue. So the next thing we need to do, if we go back and we look, let me clear some of this stuff off from here. So we look at our system here, and so we've eliminated x1 from the second one. We now need to eliminate x1 from the third equation. Looking at it over here, we can see that we've eliminated x1 from the second. We now need to eliminate this number here. So we can say, well, we've got a pivot of 2, we've got a coefficient of -2, so our multiplier would be -1. And so if we come over here, there's our multiplier, -1, and remember we've got a subtraction here, and so that's why we end up with a positive here. And so this is the same idea. This position is it's in the third row, and that's because we're talking about creating the third equation from the third equation, a new third equation from the existing third equation, and it's working with equation 1, so that tells us that we need the first column. So third row, first column, and we put in the negative of the multiplier. So the negative, or the multiplier is -1, so we put in a +1. Let me clear that off here and then proceed. So if we take that multiplier, or I'm sorry, this E31, and we multiply both sides of our previous equation. So let me back up. So we take this matrix here, multiply it by E31, take this vector, multiply it by E31, and we'll get this. And we see that now we have eliminated the coefficient there. We have a 0. And in this format, we now have both of those eliminated. So the next step is that we want to eliminate the x2 from the bottom one. That means we need to focus on this, and it's this machinery that we're going to use, because nothing will happen out here when we add and subtract. That's the kind of part of the mechanism here. So we need to just go up to the first equation that has zeros all the way up to where we're working. And so our pivot is 1, our coefficient is 1, so 1 divided by 1 is 1, and we need to subtract, so we'll end up with a -1 there. And so we call this E32, and you can see that the 3 and the 2 come from indicating which equations we're using to make this happen. Notice that the notation for the elimination matrices doesn't indicate what the multiplier value is. It just indicates where the multiplier position is. So in reality, there are many different elimination matrices. So E31 doesn't have to have a 1 here. It can have whatever value is necessary there. So that's how that works. And so if we apply this to both sides, we now have our upper triangular matrix here. We have our new resulting B vector. And that's the system that we can solve. So then we can solve this bottom one, get a value for x3, back substitute that into this one, get a value for x2, back substitute both of those into this one, and get a value for x1. So let's formalize the form of this elimination matrix. I've been saying it as we've been going along, but we'll actually write down the rule here. So as I alluded to, we start with an identity matrix, and basically we're going to find one of the lower zeros, and by that we mean the zeros below the main diagonal. So we're going to take one of those lower zeros and replace it with a value that is related to the multiplier. And so here's the big yellow box with the red ink in it. That's always a clear indication that this is something important. So the elimination matrix E sub ij, this is the matrix that does the action that will subtract a multiple L, so our multiplier will be L, of row j from row I. So notice that it's those are the things that give us the subscript on this. But also notice that that tells us the position where we're going to put the multiplier. And in fact, what we put there is not the multiplier, but the negative of the multiplier. So see here it says subtracts a multiple L. So the subtraction gives us the negative sign, the multiple L gives us the value. So if the multiplier ends up being negative, we'll end up with a positive number in that position. So there is something that subtracts 2 times the first row from the second row. And then this one, E31, subtracts negative 1 times the first row from the third row. And then here's E32, and this one subtracts 1 times the second row from the third row. So it's pretty straightforward to form these things. You just need to do a little bit of practice and you should have it nailed down. Now, the other thing that we needed to do when we were solving by elimination was sometimes we ended up with a zero pivot, and in some cases that led to a permanent failure, and that was the case. That would indicate the case that we either had no solution or infinitely many solutions, and it wasn't fixable. But for the case where there is a solution to the problem, we still may end up, as we go through the elimination, having at least temporarily a zero pivot, but we can fix that by recognizing that if we just interchange 2 rows, suddenly we're back in business, so to speak. And so a permutation matrix will allow us to interchange 2 rows of the equations. So here's a case. Maybe we start this way, or we ended up this way after doing some elimination. So maybe after our first step, or maybe after our second step of elimination, this would have to actually happen after our first step. But we end up with both of these having been canceled, and we, maybe we had that as part of the system that was not there. But now to proceed, our rule would be to look here for the pivot. So the pivot is 0. So the pivot is right there. We're looking to cancel this to get into upper diagonal or upper triangular form, but we can't have the pivot 0, and so that leads to a problem, but it's a fixable problem. All we've got to do is switch. So looking at it from the equation point of view, let me get rid of the ink here. If we look at it from the equation view, if we interchange these 2 equations, so put the last one as the middle one and the middle one as the last one, then we're back in business and we've got no more business to do. We're done. We have an upper triangular form. Same thing here. If we interchange those two rows and those two positions, and remember we have to, well, yeah, I mean, that's all we would really have to do is interchange those. We don't have to do anything with the X values. They don't really move. Because remember, they're folding over here, here, and here. So once we do that, that interchange, we're back in business. But remember, we're trying to do all this with matrices so that we can have a nice matrix representation of how to do this. So that we could easily do this numerically in a computer. Just tell it, form the matrices this way and do the multiplication, and it does it. So the claim here is that to do that interchange, we would use this matrix. And I would encourage you to take this matrix and put it here and put it here in front of the B and see the action that it does. And you can see that it will interchange the second and third rows of these things. And so when we do that, we end up with this. And for this problem, that's all we have to do. But in other problems, we might have to do some eliminations first, and then we discover this scenario, and we then craft the correct permutation, apply it, and then proceed from there. And we may need some further elimination steps after switching. So let's formalize the form of the permutation matrix. So remember, the elimination matrix, we started with an identity matrix and we changed one of the lower zero values into the negative of the multiplier. Well, here there's no multiplier. We're just trying to interchange. But we start again with an identity matrix, and we just take the identity matrix and switch its two rows that correspond to the two rows that we want switched in A and in B. So it's easy to say that. Here's the big yellow box with the red ink inside. So the permutation matrix Pij exchanges rows I and J. So we start with the identity matrix and we interchange its I and J rows. So here's P12 that is going to exchange the first row and the second row. So, we started with a 1, and this was 0, and this was 0. So if we interchange them, the one that was there goes to here, the one that was here goes to there, and you can see that that is indeed what we have here. Third row stays where it is because we're not interchanging that with anything. And there's P13, and there's P23. So, regardless of how many equations we have and which ones we're interchanging, it's pretty easy to figure out what they are. Now, remember I said that the E matrices were, so if I said E12 for a given size, maybe 3 by 3, that was not unique because it doesn't capture the value of the multiplier. But the permutation matrices are unique. So for a 3 by 3 case, P13 will always look exactly like this. There's no value that has to be included in there. So once you know how to form them, you know exactly what they are. So now we get to this concept of the augmented matrix. And all that does is allows us to mechanize this a little bit more simply. So when we were just doing this idea, we were saying, hey, apply either the elimination matrix or the permutation matrix to A, apply it to both sides of the matrix equation. And so we would apply it to A on the left side and apply it to B on the right side, and we get a new A and a new B. But it turns out that it's what we can do is form what we call the augmented matrix. So we take the A matrix and the B, and we put both of them into a single matrix. And again, this vertical line here, that's just notational. There's nothing significant about that vertical line other than it just helps us visualize that we've put an A on one side of it and the B on the other side. Some books might not even put that line there. And so now, one reason that we introduced the idea of block matrix multiplication is that we can now easily figure out how to multiply EIJ times this. But there's another view that we had. Remember, we talked about the linear combination view, or at least this is the first part of the first step of the linear combination view. We said we can pass this through to each of the columns. Well, we're just going to pass it through to A, and we're going to pass it through also to B. So we get something that's on the left side of the partition, that's our new A, and we get something that's on the right side of the partition, that's our new B. And if you remember, A is square, E is square, so this will end up being the same size as A. This is square, and this is a column vector, so this will end up being a column vector, same size as B. So we're in business. And so the whole point of this, there's nothing big here, there's no real big deep idea. It's just a simple way to kind of put everything together and just do one fell swoop. So if you were writing code to do this, you would just tuck A and B into a matrix, and the augmented matrix, and then apply either your elimination or permutation matrix as necessary to the augmented matrix, and you'd end up with the new augmented matrix. So it would just be one step that you'd have to do. And so that's kind of the point of this. So here's an example of doing this. So you should be able to work through this by hand and verify that this actually works the way that it does. So we start off with our original matrix equation, and from that we form this augmented matrix. Now notice that the augmented matrix is no longer square. So it's actually always a short matrix because A is going to be square, and then we're adding one more column, so it has one less row than we have columns. So it's always a just barely short matrix. And so now to apply our first elimination matrix, we see that we want to focus on this. There's our coefficient. Here's our pivot. So we're going to take 4 divided by 2 to get the multiplier. So 2 is the multiplier, and then we put the negative in front of it to enact the subtraction part of it. So there's our elimination matrix, and if we multiply that, we see that we eliminate that. These numbers get changed accordingly, and this number gets changed accordingly. But everything else, the top row and the bottom row in this case, remain the same. And then we could continue doing this, and I would encourage you to check this out and see how it works, using the by hand approach of matrix multiplication. And we ultimately end up with something that looks like that. And then at that point, we could separate them out. We could split out the A from the final A from the final B, and work with those separately at that point if we wanted. But there are ways to kind of work with this together to find the solution. So here are some exercises, and I would strongly encourage you to pause right now and try your hand at these. These are not tricks like I gave in the earlier set of notes. So you should be able to, armed with what you have seen already, be able to answer these things. So you should pause the video and then come back, and I'll go through each of these exercises. Okay, so hopefully you gave that a shot and didn't look at the notes that were posted, because really, if you have to look at them, If you're totally stumped, that's fine. But there is some value in just sitting there, scratching your head, wondering. If you give up too easily, you're not going to get the benefit. But if you're just completely stymied, perfectly fine to take a peek and maybe try to get a hint. But trust me, if you take the approach of, well, I'm just going to read through the solution rather than try it myself, that'll be good enough. My experience is that that's nowhere near as good as struggling a little bit trying to do it. But these are not challenging problems to begin with. So here's the problem. Just find E21 that subtracts 4 times row 1 from row 2. So the row 1 and the row 2, that's what gave us the 2, 1 here. The subtracts 4, that's going to tell us the value of the one element that's changed in there from the identity matrix. So the place where that's going to be is in the second row, because we are trying to create a new row 2. So we know that that's going to change. And so everything else is the same, or the top and bottom rows. And the subtracts 4 times row 1 tells us that we need to put a -4 in there. So remember, the row 1 is telling us that in the matrix we need column 1. The row 2 here is telling us that we need it in the position of row 2. So that's how we end up figuring out where it goes. And subtracts 4 gives us the -4 that's there. Now the 2 remaining question marks there, well, they're the same as we would have for the identity matrix. So in reality, notice that we really should have known all of this already, because all of the elimination matrices, the only thing we can do is change one of the zeros that's below the diagonal. So for a 3 by 3 case, we know this is going to be 1, 1, 1, 0, 0, 0. We know all of that. We just don't know what's here. And then, like I said, the row 2, the thing that we're trying to change, tells us the row of the matrix, and the row that we're using to make the change tells us the column. And so that's where we figure it out. And then the subtracts 4 tells us the -4. So there's our final answer for that. The second problem was what matrix, and let's just call it P32, exchanges the second and third row. We know that nothing's going to happen to the first row. So remember how we do this. We start with the identity matrix and we just do this operation on the identity matrix. So we're going to switch row 2 and row 3 of the identity matrix. Well, this is doing it in 2 steps, kind of showing you how this would work. But the simple thing is that this bottom row was the second row of the identity matrix, and the second row here was the third row. So they've now interchanged with each other, and that's the basic idea. And then our third problem says use those things that you just created to reach a triangular system for this set of equations. And you can see why we needed those particular things. Now notice that this last equation here is already just has 2 variables. We don't have x. So we're only going to need to try to eliminate this, and we can already see what's going to happen, right? We've got a 1 and a 2, so the ratio is 2 to 1. We've got a 4 and an 8, so the ratio is 2 to 1. So we know that when we do this first elimination, that we're actually going to encounter a 0 pivot after that first step. But since this is already has no x, it should be clear at this point that all we'll need to do is interchange. And that's where the P32 comes in. So let's work this with the augmented form. So there's the augmented form, and you can see here that I didn't put in the explicit vertical line. Sometimes it's nice to put it in, sometimes you don't have to. So there's our augmented matrix. And then we're going to apply the E21 that we had before. And if you go through the motions of doing the by hand multiplication, you'll discover that it ends up like this. And sure enough, just as I predicted, because of the same ratio, 1 to 2, 1 to 2, we get both of these canceled. So they started off as 4 and 8. So, we multiply by 4 here, and it creates a 4 to cancel there. But multiplying 2 by 4 creates an 8 that cancels there. So that's how we got the double zeros there. And then we look at that and we go, uh-oh. So here was my first pivot, and second pivot will be the, assuming that I have a 0 here, I go to the element on the diagonal, the 2, 2 element, and I go, oh, crap, it's a 0. So 0 pivot. And so immediately we ask, can I fix this by interchanging? So I look down below and I go, okay, I got a 0 down there already, and I've got a 3 here, so I can fix this by interchanging. So now if I apply P32 to that, that just interchanges. So the third row becomes the second row, and the second row becomes the third row. And that's what we have. And now we see that we have a upper triangular A, and here's our new B, and so we're good to go. And so the other thing that you'll notice is that, notice as we go through these problems, we just keep stacking up multiplications of these elimination and permutation matrices, and kind of work right to left. So the rightmost one, the one closest to A, is the first thing that we applied. Then we apply this, and if we had a bigger system or a system that needed more eliminations and or permutations, we would have another one out in front, and then maybe another one. And for really large systems, we would have lots and lots of these things here. And we'll revisit this in subsequent notes and see what this is all about. But that's kind of an important idea that will come into play in some of our future work. But for right now, you should be able to identify the appropriate elimination matrices, appropriate permutation matrices. And remember, you only need a permutation matrix when you hit a 0 pivot and you recognize that, oh, I can fix that 0 pivot by interchanging some rows. Then the permutation matrix comes to your rescue. Other than that, you don't need them. You could go through an entire problem and never have a permutation matrix that's needed. Okay, so that wraps this up, and we'll see you in the next video.